Why are black holes the most formidable celestial bodies in the universe? They are, in fact, astonishing laboratories where space-time and quantum reality collide in the most bizarre ways. From space-time bounces that may have ignited our Big Bang, to ghostly neutrino surges and quantum entanglements within the cosmic microwave background, black holes constantly challenge our fundamental understanding of the cosmos. Join me as we journey deep into the wildest and most unexpected physical phenomena surrounding these mysteries, discovering why black holes might just be rewriting the rules of existence. This is a long story, one we could dream about, but before we begin, please like, follow, and share. Scientists believe that the process of an object being stretched and torn apart as it nears a black hole known as spaghettification is not the smooth, continuous pull we once imagined. Instead, it likely occurs in short, violent bursts. In one experiment, researchers cooled atoms to ultra-low temperatures until they behaved as a single, massive wave. When they spun this ultra-cold atomic cloud rapidly, it functioned as a miniature proxy for the edge of a black hole. The results showed that the cloud did not split evenly, it fractured into tiny vortices, each emitting a burst of sound waves. This suggests that as real matter falls toward a black hole, it is shredded in rapid successions rather than being slowly elongated like taffy. In another study, scientists observed a Bose-nova, where a cold atomic cloud implodes and then bounces. For a fleeting moment, particles collapse inward before exploding violently, mimicking the chaotic destruction of a star under a black hole's gravity. These observations suggest the final stages of spaghettification are frantic and messy, not a slow stretching of filaments. Sound can also simulate these environments. By creating a barrier in a superfluid that prevents sound waves from escaping, much like an event horizon, researchers found that trapped sound waves eventually eject in intense pulses. These behave like miniature jets, implying that matter near a black hole might be spat out in rapid bursts before vanishing entirely. Rotating black holes are even stranger. Scientists have shaped a mixture of light and matter into spinning rings to simulate them. As these rings rotate, portions are flung outward, stealing energy from the rotation itself. This mirrors how real rotating black holes twist and tear surrounding matter, accelerating it to escape velocities. Astronomical data supports these findings. In 2019, when two massive black holes merged, detectors captured not only the primary collision signal but also faint echoes spaced about a second apart. These echoes may be ripples caused by matter being torn apart in short pulses at the black hole's periphery. Some theories propose an invisible stretched horizon, a sticky, membrane-like layer at the edge that catches and tugs at matter before suddenly releasing it, creating intermittent bursts. By studying these space-time ripples, scientists believe this membrane might explain the post-merger echoes. Others suggest the surface of a black hole isn't smooth but covered in fractal-like repeating structures. This roughness would cause falling matter to snag and tear in a jagged, zigzag fashion rather than a straight line, a process like a thread being caught on infinite tiny hooks. A newer perspective suggests gravity emerges from an information screen around the black hole, where every bit of data exerts a pull. In this view, spaghettification is a packet-based process rather than a continuous stretch. Soon, the LISA space mission will listen for low-frequency gravitational waves from merging black holes. Engineers expected to detect the faint, long-duration echoes that correspond to these predicted bursts. If successful, we could map spaghettification in real time, verifying whether matter tears in jumps or pulls into a long string. On Earth, high-power lasers and plasma experiments are already replicating these tidal effects by blasting thin metal foils into tiny filaments, providing a way to study these phenomena on a lab bench. Scientists have also discovered that if a black hole could somehow exist in two different sizes simultaneously, nearby clocks wouldn't just slow down smoothly, they would tick normally, then slow, then suddenly speed up, almost like a stutter. This implies that near the event horizon, time flows in leaps rather than a smooth stream. When particles with internal clocks approach a black hole, the gravitational gradient disrupts them. Imagine a wristwatch where the second hand starts jumping erratically until it loses all rhythm. This jittering stems from minute differences in gravitational pull, causing the clock to lose its beat without any external interference. Simply being near a black hole is enough to break the rhythm of time itself. In deep space, researchers measuring signals from pulsars, the spinning remnants of stars, have found subtle delayed echoes. These echoes act as a direct demonstration of how time is stretched and warped around massive objects, turning Einstein's theories into observable reality. By comparing signals from two pulsars orbiting the same massive body, scientists can even calculate the object's rotation without ever getting close to it. Closer to home, astronomers tracking the star S2 as it orbits the supermassive black hole at our galaxy's center have noted slight orbital shifts. These shifts align perfectly with the predicted changes in time flow, helping verify whether time warps exactly as Einstein described or follows hidden new laws. Some theorists even propose that space-time has a memory. As matter nears a black hole, it may leave a fingerprint in the surrounding space. If true, extreme time dilation could be recorded in this cosmic memory, potentially allowing us to read these imprints via special particles dripping from the horizon. Physicists have even simulated black hole gravity by splitting tiny particles. When they recombine, the interference patterns like ripples in a pond show shifts caused solely by the different amounts of time each particle experienced. This allows us to see extreme gravity stretching time right in the laboratory. Soon, the LISA probe will join ground-based pulsar observations to map the secret flow of time around rotating black holes. In the M87 galaxy, scientists observed plasma clumps around a supermassive black hole flickering like pendulums, but 5 times slower than distant clocks, a vivid, real-world display of time dilation at the innermost orbit. In ultra-cold liquid experiments, scientists have created acoustic black holes to trap phonons, or packets of sound energy. When these phonons eventually escape, they don't produce a steady hiss but rather intermittent, large fluctuations. This burst pattern is a hallmark of Hawking radiation, suggesting that a black hole's emissions are pulsed rather than uniform. Using the quantum Hall effect in solid-state experiments, researchers have also simulated the event horizon, detecting a steady stream of quasi-particles that follow the laws of thermal radiation, just as Hawking predicted. Each radiated particle is linked to a partner on the other side of the horizon, confirming that black holes emit a strange form of thermal radiation. When black holes collide, the signals such as those from the event GW190521 often contain Boltzmann echoes. These suggest that the energy of the merger agitates the quantum bits of the horizon, which then ring like a bell, releasing ripples long after the main impact. Some theories suggest that when a black hole shrinks to the atomic scale, it doesn't vanish but freezes into a dense Planck mass remnant. These remnants might stop radiating and persist forever, potentially making up the universe's dark matter. While Hawking's formulas show black holes have a temperature, new research suggests this heat creates a feedback loop, pushing back and altering the black hole's shape and evaporation rate. These Hawking particles aren't just random sparks, they likely maintain quantum entanglement with their partners inside. Fluid simulations have shown that escaped sound pairs remain entangled, hinting at an information coding system within the radiation that might one day allow us to retrieve what was lost inside. Telescopes are now searching for the gamma-ray flashes of evaporating mini black holes to prove this radiation exists in nature, while lab experiments using trapped ions track how information scrambles near an artificial horizon to solve the famous black hole information paradox. Some scholars propose that space-time itself possesses a quantum memory matrix. When a black hole releases a Hawking particle, it leaves a microscopic trace like a footprint in the sand. Future precision measurements might allow us to read these traces like a secret diary of the black hole. Scientists are also using optical black holes made of laser-cooled photons to observe how quantum fluctuations transform into heat. Furthermore, advanced computing has revealed that the black hole at our galaxy's center spins at nearly the physical limit, tilting its bright ring of light into a distorted halo rather than a flat circle. While we once thought black holes were as smooth as bowling balls, new theories suggest they have quantum hair-tiny imprints that record everything the black hole has ever swallowed. This means information is never truly lost. Some see the edge not as a void, but as a hot, viscous fluid membrane that drags and heats magnetic fields. Another bold theory, the firewall, suggests a high-energy curtain at the boundary that incinerates anything falling in, contradicting Einstein's idea of a smooth crossing. Using multiband imaging, the Event Horizon Telescope can now see different layers of plasma, mapping the black hole's vertical profile. They've even observed nested rings of light photons that loop the black hole multiple times, creating a hall of mirrors effect. Mathematically, the surface of a black hole behaves like matter at a critical state, which explains why its entropy is proportional to its surface area. Experiments with Bell particles escaping simulated black holes show that information follows a page curve it goes in, but eventually leaks back out, much like the pieces of a puzzle drifting out of a fire through smoke. In rotating black holes, entanglement islands may act as secure vaults for information, releasing it as the black hole decays. Whether it's through soft hair ripples or replica wormholes connecting different copies of the universe, even today's small quantum computers are beginning to simulate this evaporation, proving that the secrets of the black hole are slowly being unlocked. Scientists have constructed a black hole game on a quantum computer to observe how information bits jump and diffuse. The results revealed a pattern of entropy change identical to the page curve, marking the first time we have witnessed information returning bit by bit from a simulated black hole in a laboratory setting. A bold theory known as ER equals EPR suggests that all entangled particles are connected by hidden, microscopic tunnels. This implies that particles inside and outside a black hole remain linked through these miniature conduits, allowing information to re-emerge via Hawking radiation rather than being lost forever. String theory offers another perspective called the fuzzball model, where the edge of a black hole is not a smooth horizon but a tangled knot of countless strings. Each knot represents a different microscopic state, recording the information of all matter that entered. As the black hole shrinks, these strings gradually unravel, releasing every secret detail into the Hawking radiation. Recent comprehensive studies on various methods and quantum boundaries show that the mechanism of information leakage holds true regardless of the gravity theory used. We are now certain that as long as quantum mechanics and gravity combine, black holes do not truly destroy information, resolving a mystery that has haunted physics for decades. Scientists even envision creating a black hole chip made of tiny circuits that follow these quantum rules, allowing them to input data and track its leakage in a controlled environment. Latest mathematical breakthroughs have also refined the formulas for calculating the page curve in flat spacetime, telling us that a black hole begins releasing half of its information at roughly one-third of its lifespan. When a star collapses, the core sometimes briefly exposes itself before being completely hidden, a phenomenon known as a naked singularity. Usually, the collapsing core is veiled by the event horizon, but if the star's interior is not perfectly symmetrical, parts of the core might peek through the curtain. New theories of gravity suggest that standard equations might fail under specific conditions, causing the magician's cloak to drop and revealing the secret early. Researchers using ultra-cold fluids to simulate collapse found that shock waves often smooth out local irregularities, suggesting that nature might have built-in protection mechanisms to hide these singularities. Computer simulations show that a barrier appears at the final moment when matter and radiation mix, and only when energy conservation is disrupted does the naked singularity become exposed. Some believe signals from naked singularities may have already appeared in the universe as rapid gamma-ray bursts. The strange spikes in these bursts do not match typical black hole mergers and might carry deep cosmic secrets. X-ray spectra around supermassive objects also show anomalies. When an object spins beyond a critical point, gravity laws change, causing the iron spectrum to distort in a way that suggests a naked singularity hidden in a distant galaxy. String theory's fuzzball model further explains that there is no traditional covering, only a sphere of interwoven strings that slowly releases information. Theorists also propose that naked singularities might scream in the form of high-frequency gravitational waves, sounding like sharp, high-pitched notes. Some singularities might not tear matter instantly but instead crush it slowly and flatly, meaning not all of them are as terrifying as imagined. At the moment a black hole finally evaporates, its cloak and hidden core meet and vanish simultaneously, like the final act of a play where the backstage is briefly exposed before the lights go out. A clever mathematical trick shows that wormholes could be kept permanently open. Usually, a wormhole collapses too quickly for anything to pass through, but a quantum connection between two distant regions could stabilize the tunnel without needing exotic matter. When a small black hole passes through such a wormhole, it emits space-time ripples with a reversed frequency, a phenomenon called an anti-chirp. If we detect a siren that grows fainter rather than sharper, it might mean a black hole took a shortcut through a wormhole. Gas and dust around a wormhole would form ring structures with bright spots rather than a smooth disk, and light might circle the entrance multiple times to form multi-layered rings. Quantum computers are now powerful enough to simulate a simple wormhole on a chip, successfully sending a bit of quantum information through a simulated space-time channel. This reality test of Einstein-Rosen ideas shows that space can be a smooth tunnel rather than a distorted pipe. Wormholes might even leave permanent imprints in space-time, causing particles to shift slightly out of place after a gravitational wave passes. Some propose that aging black holes might reverse into white holes at the end of their lives, exploding with new life rather than fading away. Matter and time pressed into the interior would be thrown back into the universe, with the black hole spitting out everything it once swallowed. Scientists have already simulated this flip in the lab using lasers and special materials to create optical white holes. This suggests that matter falling into a black hole might hit a cosmic speed bump and bounce back, allowing the transformation without violating physical laws. Short gamma-ray bursts might be the birth cries of these white holes, releasing intense energy that traditional theories cannot explain. In loop quantum gravity, black holes might leave stable, microscopic white hole remnants that store all entering information and mass, potentially acting as a strange form of dark matter. Some even suggest that quasars are actually white holes in disguise, pushing energy outward rather than pulling it in. By simulating spin waves in magnetic superfluids, researchers have seen reflections that mimic white hole boundaries, suggesting these laws are universal. At the smallest scales, Space-time is not a smooth fabric but a churning foam of quantum fluctuations. Black holes might magnify this foam, acting as natural laboratories for the deepest structures of reality. Astronomers use gamma rays to test for this foam, looking for tiny delays in photon arrival times. While current observations suggest the foam is smoother than expected, future detectors may reveal its details. This foam might be the source of the Big Bang itself, one bubble among many that expanded into our universe. Within the holographic framework, quantum foam represents the smallest units of information, the source code of space-time. Today's journey ends here. May you have beautiful dreams, and I will see you in the next episode.